Welcome to our lesson on factorising polynomials. So last lesson we looked at dividing polynomials. So these two things do go hand in hand. Now in the past you've factorised quadratics and you have probably a few different techniques to do that. But we can also factorise higher degree polynomials with some pretty simple techniques. So cubics, for example, we can factorise. There are two theorems we're going to look at today. The first one's the remainder theorem and the other one is the factor theorem. We'll probably use the factor theorem a little bit more, but we'll go over the remainder theorem first. Before we do that, remember this little note just here. We spoke about this last lesson and the lesson before. So remember, if f of x, so some function of x, is a factor of our polynomial p of x, then our polynomial divided by our function of x will leave no remainder. So in order to break something down into its factors, there shouldn't be a remainder. You're just splitting up a polynomial into two things that can be multiplied together to get to your polynomial. Okay, so the remainder theorem states that if we divide our polynomial p of x by x minus alpha, so this little symbol here is alpha, looks a little bit like an x, also looks a little bit like an a, so don't get confused if you're reading that or writing that. So if we divide our polynomial x by x minus alpha, then our remainder of x should be equal to p of alpha. So basically, if we sub alpha into our polynomial, and if x minus alpha is a factor, then our remainder of that polynomial should be equal to the polynomial alpha. Okay. Now, let's have a think about that because it is a little bit confusing just saying that and reading it. All right, so we've got p of x. Now, we know p of x, based on the identity we worked out last lesson, can be broken down into our divisor and our quotient plus a remainder polynomial. Okay, the theorem is stating that we're dividing p of x by x minus alpha, and our remainder should be equal to p of alpha. So essentially, if we're subbing alpha into here, that's what our remainder should be equal to. So r should just be equal to this, but at the moment we've got all of this. So essentially what that theorem is saying, that all of this should be 0. In order for our remainder to equal our polynomial, all of this has to be equal to 0. Now, the only way we're going to get that equal to 0 is if one of these factors, is equal to 0. If one of these is equal to 0, they're being multiplied together, then 0 times by, doesn't even matter what this is, the whole thing is going to go to 0. So in order for this theorem to prove true, we have to somehow have this equal to 0. Now, our theorem also states that we're dividing p of x by x minus alpha. So we know that our divisor is actually x minus alpha. We still don't know what the quotient is, and we have this remainder. We know the remainder has to equal p of alpha. So if we had p of alpha, whenever we see x, we're going to replace, whenever we see x, which is what this is telling us, we're going to replace it with an alpha. Then over here, I would have alpha minus alpha. Q of x plus r of x. Now that makes sense. Alpha minus alpha is going to go to 0, which means this whole term here is going to go to 0. And we have p of alpha is equal to our remainder of alpha or our remainder of x. They're equal to each other. So that's kind of a little bit of a weird way of proving this theorem over here. So the theorem's telling us that if we divide p of x by x minus alpha, then our remainder is going to equal to if we sub alpha into our polynomial. So putting alpha where the x should go. It can be written in a different way as well, and the textbook writes it this second way. It's exactly the same thing with the same sort of proof, but they've written it as if you divide p of x, your polynomial, by beta, this weird looking b with a tail, x minus alpha, then your remainder is P of alpha divided by beta. The exact same proof, and it makes sense if you subbed in, if you were dividing by beta x minus alpha, and that's what your remainder should equal to P of alpha over beta. If we subbed in alpha over beta into our x, alpha over beta, you would end up with beta cancelling out, alpha minus alpha, that would go to 0, and hence the same process that we saw above. So that's kind of a little bit of proof behind the theorem there. So, but that's the theorem, and that's the thing that we're going to use. And it works out really nicely, and it helps us answer questions that say, what is the remainder when you divide this by this? So it helps us really easily do that without having to go through the whole process of division and then work out what the remainder is at the end. It helps us skip that process of revision and just get the remainder, because sometimes that's all the question is going to ask. So we can use this nice little remainder theorem to help us do that rather than do the whole process. All right, so let's have a little bit of a go. Calculate the remainder when P of x is equal to this lovely polynomial here. And that's divided by x minus 3. Let's give ourselves a little bit of room. Just bear with me for a moment. Okay. All right, so we're going to calculate the remainder when P of x is divided by x minus 3. So we could rewrite that as P of x. We know it's our divisor, times our quotient, plus our remainder. The theorem tells us if we divide P of x by x minus alpha, then our remainder is equal to P of alpha. So in this case, if P of x is divided by x minus alpha, then our remainder is going to equal to P of alpha. So in this case, we're dividing by x minus 3. Now that's in the same format as x minus alpha. So we could say, okay, using this theorem, my alpha is equal to 3. That means my remainder is going to be equal to my polynomial when I sub 3 into it. So my remainder should equal to 3 times 3 cubed plus 4 times 3 squared minus 7. Subbing 3 into there, our answer would be 110 if you were to go and work out all of those individual bits. So there you can see that you can work out the remainder really, really easily using this theorem without having to go through the whole division process and then working out what the remainder is on top of that. So it's quite nice. So I'd like you guys to have a go at this one. So pause the video, have a go at that one, and come back and check your answer. Okay, so you should have, if P of x, as our remainder theorem states, is divided by beta x minus alpha, so this is the one that's more relevant in this case, then our remainder should equal to our polynomial if we sub alpha over beta. So that's just your remainder theorem up here, but the other version of the remainder theorem. All right, we have our divisor written in this format. That's why we've chosen this format of the remainder theorem. So we could say, well, in this case, my beta would be 2, and my alpha would be 3. So then I can say, well, my remainder then must be equal to my polynomial when I sub my alpha over beta, so 3 over 2. So subbing 3 over 2 into that polynomial, you would have, so 3x cubed, 3 over 2 cubed, plus 4x squared minus 7. Your remainder would be equal to, your remainder should be equal to, if you sub that into your calculator, or you could work it out manually, 35 over 4. So again, working out the remainder without really going through the whole division process. Now, for the sake of time, guys, we're not going to completely go through part C, but absolutely have a go at it in your own time. It's the same sort of technique. So there's another one there that you can practice with. Okay, so we've been through the remainder theorem. So the remainder theorem is a really nice little simple technique to help us work out the remainder without doing a big division process. So now we're going to look at the factor theorem. The factor theorem states, if x minus alpha is a factor of our polynomial p of x, then p of alpha must equal to 0. Let's unpack this a little bit. If x minus alpha is a factor of p of x, then p of alpha must equal to 0. So keep in mind, we can write our polynomial, and we've done this a lot now, as our divisor multiplied by our quotient plus our remainder. However, we're factorizing. We're assuming there is no remainder. So in order to break something down into two factors, there is no remainder. Otherwise, we're not factorizing. Okay, and it's saying x minus alpha is a factor. So we know that one of these things, the divisor or the quotient, is x minus alpha. So let's just say, well, p of x is equal to x minus alpha times by q of x. We don't know what our quotient q of x is, but it doesn't really matter because the next part of the theorem states that if this is true, if x minus alpha is a factor, then when we sub alpha into our polynomial, we should get 0. So let's have a try. So subbing alpha, wherever we see x, we would have alpha minus alpha. Hey, look, that goes to 0. Now, if that goes to 0, 0 times by the quotient is still 0. So we would have p of alpha is equal to 0. So it's true. That's kind of the reasoning behind, or a little bit of proof for the factor theorem. So we can trust it. We can trust that this factor theorem works. So if x minus a is a factor of our polynomial, then if we sub alpha into our polynomial, our answer should be 0. And we can use that kind of in a backwards way to solve some questions as we go on. Just like the remainder theorem, the textbook writes it slightly differently. It means the same thing, but we've got bx minus alpha as a factor, then we're subbing in alpha over beta into our polynomial to get 0. You pick and choose what works for you for each individual question. Okay, let's have a look at an example. So we want to show that x minus 2 is a factor of this polynomial here, and then hence fully factorize p of x. But the first bit, showing that x minus 2 is a factor. Our factor theorem states, if x minus alpha is a factor, then when we sub alpha in, we should get 0. X minus 2 is written in that same format, x minus alpha. So we could say, well, our alpha in this case is equal to 2. So if I sub my alpha, my 2, into my polynomial, what should my answer be? My answer should be 0. In order for this to actually be a factor, if I sub that 2 in, my answer should be 0. And if we can show that that's equal to 0, then we've shown that x minus 2 is in fact a factor of this polynomial. So subbing in 2, we have 2 times 2 cubed minus 7 times 2 minus 2, 2 times 8, 14, 2, 16 minus 14 minus 2, and look at that, we have P of alpha, or P of 2, is equal to 0. Therefore, x minus 2 is a factor due to the factor theorem. And that would be for working out there. The question's not completely done. It says that we have to fully factorize P of x. Now, this is just going back and using those techniques that we learned the other day. So we know x minus 2 is one of the factors. We know P of x is equal to our divisor times by our quotient. We don't have a remainder because we know it's fully factorized. It's fully factorized, there's no remainder. We don't have to add that remainder on, which makes it really nice. We know that our divisor is x minus 2. We just have to work out what this quotient is. Just like the other day, in order, our original polynomial is a cubic. This is a linear. This one must be a quadratic in order for the first one to be a cubic. So again, ax squared bx c. We chuck in our polynomial over this side. I haven't left enough room to do that. And we expand, collect our like terms, and equate our coefficients like we did the other day. So you guys should be pretty familiar with that process. I'll come back at the end and write the answer down here if you would like to have a go at it. Otherwise, we're just going to move on for now. This is all yesterday's content, and you can flick back and see the answer later. Okay, here's a couple more you can have a go at. So we want to fully factorize this one here and this one here. So a couple of examples there you can have a go at. Pause the video, check back, and see if you got your answer correct. Now guys, for the sake of time, I'll pop these solutions up on the OneNote so you can go and check over there if you got them correct. One last thing I wanted to mention were some very special cases of using these theorems and factorizing our polynomials that are a higher degree than a quadratic, and they make our life really simple. So if you ever have the scenario where your polynomial is simply x cubed minus a cubed, then you can say straight away that x minus a is a factor, and the quotient, the other factor, is going to be written in this format. So that's really, really nice. And it also can be written in the positive scenario version of that as well. What that means is, say if you had x cubed minus 27, oh hey, I've recognized that 27 is simply just 3 cubed. So I have x cubed minus 3 cubed, which is this scenario up here. Well, my a is equal to 3. Therefore, I have x cubed minus 27, so x cubed minus 3 cubed is equal to subbing 3 for our a value in the rule that we saw above. So there are special cases. They make our life a little bit easier when you have special cases like this. So you don't have to go through the whole process. Okay, textbook work today is exercise 8C. The particular questions that you have to do will be up on the OneNote. Have a look there. This stuff can be a little bit confusing, but once you wrap your head around it, it's really not. You'll kind of do questions over and over, and you'll find them pretty simple after a while. But good luck, guys. Have fun.